This talk is about looped waves in the medium of space. Now, thinking of space as a medium arises when we realize that as a result of the LIGO experiment, we have to think of light as a wave in the medium of space. This is because LIGO has shown through multi-messenger astronomy that gravitational waves and electromagnetic waves travel at exactly the same speed, and we know that gravitational waves are waves of distortion of the space medium. So the same applies to light. And so starting from the premise that light is a wave in the medium of space, we move on to conclude that neutrons, protons, and electrons must be looped waves in the medium of space. We'll understand more about the nature of these waves, but what we're attempting to do in this presentation is to determine the number of wavelengths in the loop for the three fundamental particles, which are the neutron, proton, and electron. And to do that, we're going to use the mathematical relationships between energy, mass, frequency, and wavelength, shown here. E equals mc squared, E equals hf, where h is the Planck constant, and f lambda equals c. So the frequency times the wavelength is equal to the speed. So first of all, applying this to the proton, the mass of the proton is given here, 938.272046 million electron volts. And we can use the mass in that form because it is essentially units of energy, and the Planck constant is in units of eV seconds. So when we use the formula E equals hf, we get a frequency of 2.268731 times 10 to the power 23 seconds to the minus 1 for the frequency. And from that, we can directly get the wavelength, which is 1.321409 times 10 to the minus 15 meters. So that is the wavelength of the wave in the proton loop. So here we can visualize what is the proton. So we think of a wave of compression and expansion of the medium traveling at speed c. So the medium is not moving at that speed. What is moving is the wave disturbance. And what we want to find out is the effective radius, which is the midpoint of this looped wave. But we've got a clue as to what that should be because we can quite accurately determine the charge radius for the proton. And that is given here, which is 0.841419 times 10 to the minus 15 meters. And so that charge radius is going to lie effectively outside the proton. So then, if there are x wavelengths in the loop, x times lambda gives the perimeter of the loop. So that's equal to 2 pi r. And from that, we can calculate x, which is very slightly over 4. But because we want an effective radius to be significantly less than the charge radius, we must have 3 wavelengths. And from that, we then get an effective radius of 0.630926 times 10 to the minus 15. So here's an illustration of the wave of the proton. So here is the effective radius, and the wave is traveling in the loop at the speed of light, and there are 3 wavelengths. So these marks here denote the breaks in the 3 wavelengths. And this is interesting because it's consistent with some scattering observations which show a 3-fold symmetry in the proton. We can do a similar calculation for the neutron, and we find that the neutron is also 3 wavelengths. So now this table shows the masses of the neutron, proton, and electron for comparison, and the frequencies, the characteristic frequencies and wavelength. And the radius, this is the effective radius of the neutron, the effective radius of the proton. Now, for the electron, I've shown, for comparison purposes, the radius of the loop when it's at 3 wavelengths, which is not normally the case, in fact. This would occur immediately after the beta decay of a neutron into a proton and an electron. But we'll see that the electron can freely increase the number of wavelengths in the loop without change of energy. So what's the difference between the proton and the neutron? So what is proposed is that the wave is not, for the proton, is not totally symmetrical. So there is a net compression within 1 wavelength of the medium of space. And that is because the wave spends a longer period of time in one state of compression or expansion than the rest of the path. So we get an asymmetry here in the wave, and that has the result of creating a net compression or a net expansion of space, which occurs in the electron and the proton, and that is the cause of electric charge. So now we can, this is illustrating the electron, which can increase or decrease the number of wavelengths in the loop without a change of energy, and we can kind of illustrate the process of capture of an electron from this diagram here. And what happens, in fact, is that the electron finds that there is a particular energy state which is stable, and so the loops of the electron around the nucleus form particular energy levels. And the reason for that is that the wave of compression and expansion follows a path around the nucleus, but as it reaches to the adjacent point, we've got effectively compression and expansion, which corresponds to positive and negative charge within the wavelength. And so the next orbit of the wave tries to adopt a position which is half a wavelength displaced, so that we get compression next to expansion and expansion next to compression. And what we know we've known for a long time is that hydrogen has specific energy levels, and we give the energy levels a value n equals 1, 2, or 3, and we can begin to see the cause of these energy levels in the sense that the looped wave can only adopt a limited number of positions. So thinking of the electron as a wave, we discard the idea of the quantum jump of a particle, because it's not a particle, it's a wave. And that wave, when it absorbs wave energy from a photon, can jump up to the next level and adopt a stable state here. So we're going to calculate the energy levels. And to do that, we're going to use the formula which was first calculated by Balmer more than 100 years ago. And that's the Balmer formula for the wavelength of the light which is emitted by hydrogen. And what he found was that he could reproduce all the different characteristic wavelengths of light coming from hydrogen by this formula where m and n are integers. So what this calculation is showing, that to produce that formula for the wavelength, the formula for the energy of the nth level must be of the form the total energy of the electron minus the ground state divided by n squared. And the rest of this page is describing how that calculation, how that formula, using m and n, results in the Balmer formula for the wavelength of the change in energy level, HF2 minus F1. So at the end of this page, we've established that the energy of the nth level is of the form ET minus EGS over n squared. So now we define Sn as the path length of the wave, Xn is the number of wavelengths in the loop, and lambda n is the wavelength of the electron. So Sn equals Xn times lambda n. That's simply saying that if we multiply the wavelength by the number of wavelengths in the loop, we get the path length. And so using that, we can derive a formula for Xn. And we know that Xn must be a whole number of wavelengths for all possible values of n. And that then places constraints on Sn, and we must have the case that Sn is equal to n squared times S1. And we substitute that into the formula, and we get this expression for Xn. And you can see that that then, given the values of the energy of the electron and the ground state, we can turn that into a formula where K equals 37565 n squared minus 1, where K is S1 EGS over HC. So we've got a formula for the number of wavelengths in the loop. Now we're going to put K equals 1, and I'll explain why later. And we also find that we need to adjust the formula to take into account the binding energy, because ultimately what we need is a formula with this number here being a perfect square so that we can factorize it. And in order to do that, we need to have binding energy of 3537.7 electron volts. And that's the difference in mass between the free electron and the electron in energy level 1. So now we've got a formula here which we can factorize, and this formula can be factored into 192n squared, 192n plus 1, 192n minus 1. But we need the number of wavelengths in each orbit to step on by half a wavelength. So we're going to divide this factor by 2 and multiply this factor by 2. And so now we've got some specific values. When n equals 1, there were 96.5 wavelengths in each orbit and each encirclement, and 382 encirclements. And so the reason we needed to choose k equals 1, because that's the only way we can get the number of wavelengths in the encirclement to step on by half a wavelength. So finally, we've got some definite results here, which shows a radius a radius of the first shell for the hydrogen atom. And this seems to match reasonably well with the atomic separation of the hydrogen molecule. So this is about half of the separation. So that concludes the main part of the presentation, but just stepping back from the detail, we can see that this way of looking at the structure of the atom based on waves rather than particles resolves a lot of conceptual issues. And we've touched on the fact that it's compression and expansion of the medium, which is the cause of electric charge. And for the proton and the neutron, we can see that those looped waves in proximity will be aiming to position space compression alongside space expansion. And that is the fundamental cause of the strong nuclear force, which is basically a force delivered by the medium due to medium compression and expansion. So this formula for the number of wavelengths in the loop has been derived without recourse to quantum theory and starting from the point of view of waves rather than particles. And this is a big step forward in terms of unification.